Have you ever wondered how these massive companies build systems that just don't seem to fail? Well, today, we're going to break down an expert's playbook, step by step, to see exactly how you design a billing system from the ground up for a huge phone company. Let's jump right in. So, here's the big question. Someone hands you this problem. 50 million phone users. They all make calls, and they all need a bill at the end of the month. I mean, where do you even start? It feels impossibly complex, right? But the very first step an expert takes is actually surprisingly simple.
Before you even think about writing a single line of code, an expert's first move is to narrow things down. You just can't build everything all at once. It's all about asking clarifying questions to go from a vague problem like build a billing system to a really concrete list of things the system absolutely has to do.
And that first set of questions, well, that gives us our functional requirements. You can think of these as the verbs of the system, the actual actions it needs to perform. What's its core job? This is all about figuring out what's in scope and, just as important, what's out of scope.
Okay, so this gives us some real clarity. The system has to do three main things. It's got to capture call records, it has to calculate the bill from that usage, and then it needs to hand that data off to some other service that will actually create the bill document. But look at what's excluded. This is huge. We are deliberately not building a system to track data usage or to process payments. Defining those boundaries right from the start, that's a critical pro move.
So once we know what the system does, we've got to define how it does it. And these are the non-functional requirements. If the functional ones are the verbs, then these are the adjectives. They're the qualities and the constraints that are going to shape every single big decision we make from here on out.
And for a system of this size, these qualities are completely non-negotiable. It has to be scalable for all 50 million users and more. It's got to be highly available because you can't just lose billing data, right? It needs to perform its main job, making a bill, within 24 hours. And of course, with all this sensitive personal info, it has to be secure. These four pillars are going to guide the whole design.
All right, with our goals locked in, the next step is to get a feel for the numbers. And look, this isn't about getting a perfect, precise calculation. It's about understanding the sheer magnitude of the problem. These quick, back-of-the-envelope estimates are what separate a design that just looks good on paper from one that can actually work in the real world.
It all starts right here. 50 million subscribers. This is our baseline, our ground zero. Every other calculation we're about to make is going to flow from this one number.
So what kind of traffic does that actually generate? You always want to plan for the worst case. So let's just assume that on a really busy day, each one of those users makes 10 billable calls. That's 500 million call records our system needs to take in and process every single day. That's the peak load we have to build for.
And if you zoom out to a whole month, what's the total amount of data we have to crunch through? Well, the system is going to process a staggering 1.5 billion, with a B, individual call records just to generate 1 month's bills. This is the number that really makes that data storage challenge feel real.
So here's the takeaway. These aren't just big, scary numbers to impress you. They're design constraints. The decision to handle 1.5 billion records versus, say, 1.5 million, that fundamentally changes everything. The technology you choose, the way you store your data, and how you process it.
Okay, now we know our goals and we've got a handle on the insane scale of the data. Now we can finally start sketching. And we're not getting lost in the tiny details yet. This is all about drawing the big boxes and the arrows to map out a high-level blueprint for the whole system.
And this really shows the core flow beautifully. The system has two main inputs, the database with all the phone calls and the database with all the customer info. The billing service is our engine right in the middle. It pulls from both of those inputs, works its magic, and then writes the results out to our final billing database.
Okay, here's a little pro tip for reading system diagrams like this one. When you see an arrow drawn from the call records database to the billing service, it doesn't mean the database is just sending data on its own. It simply means that information is flowing in that direction, even though it's the service that's actually asking for it. It's a subtle distinction, but a really important one.
All right, let's zoom in on what is probably the hardest piece of this puzzle, that gigantic call records database. How on earth do you design a system that can handle 1.5 billion records without just grinding to a halt?
Let's frame it like this. To generate your monthly bill, the system needs to find your, say, 300 calls from the last month. But it has to find them inside a database that contains 1.5 billion other records.
Now imagine trying to do that for millions of customers all at the same time. Yeah, that's a massive performance bottleneck just waiting to happen.
So what's the solution? Well, you don't search through one giant database. You break it up. The answer is a technique called sharding. It's basically about partitioning that massive database into lots of smaller, much more manageable pieces. Instead of searching for a needle in a single gigantic haystack, you're now searching for a needle in a bunch of small, easy-to-manage piles of hay.
And there are some really clever ways to do this. You could shard by area code, for instance. But then you might think, well, what if one area code is way more populated than another? No problem. You can just combine sparse areas into a single shard or subdivide the really dense ones. Or, for a really even distribution, you can use a mathematical hashing function on the phone number itself to decide which little database shard their data lives on.
But here's the thing. Solving the data storage problem is only half the battle. The billing service, that engine that actually does all the work, it also has to be able to process millions of bills at once. We need a design for our engine that's just as scalable as our database.
And the solution here is a classic, really powerful pattern. You have one thing called an orchestrator. Its only job is to figure out all the bills that need to be generated and put each one as a job into a job queue. Then you have an army of workers. They're just simple compute instances. Each worker grabs one job from the queue, processes it, and then goes back for another. And the beautiful part? If the queue gets too long, you just spin up more workers. It's like having an elastically scalable factory for generating bills.
So we have our blueprint. We've figured out how to solve for data storage and data processing. The final step is to circle all the way back to the beginning. Let's hold our design up against those original non-functional requirements and see how we did.
And it looks like a clear win. So how did we solve for scalability? With database sharding and our army of elastic workers. What about availability? Well, with data redundancy and multiple service instances, there's no single point of failure that can take the system down. And security? The whole system is internal, protected by firewalls, and we can encrypt the data. I'd say the design holds up really well.
We've designed a really solid system, but no design is ever perfect. Thinking like a real engineer means you're always looking for that next potential point of failure. The database and the service are scaled, sure, but what about the network between them? Or the job queue itself? What other hidden bottlenecks could bring a system like this to its knees? That's the kind of question that keeps the best engineers innovating.